Okay, we're going to talk about now orthogonal expansion, which will lead us to Fourier series, at least as one example of an orthogonal expansion. Before we get there, or to talk about orthogonal expansion, we need to talk about these things: inner product and orthogonality mostly. Here's what we mean by an inner product, and here's our notation for it. Something we do with two different functions. So this is the inner product of function f1 and function f2. Means we put them in this integral. f1 times the complex conjugate of f2. We take the definite integral over the interval a to b. So this would be the inner product on the interval a, b. That's what we call the inner product. If you take the inner product of a function with itself, you get what's called the squared norm of that function. If the inner product of two different functions is 0, we say those two functions are orthogonal. This is all on the interval AB, where I'm using this overhead bar to mean complex conjugate. And we just reviewed complex numbers, so I can skip that. Let's do an example. Let's see, is this function f1 orthogonal or not to this function f2 on the interval -1 to 1? So let's just see. Well, their product is, let's see, x to the 5th plus x cubed. We put that in our, they're both real, so yeah, we don't have, so the complex conjugate of f2 is x squared plus 1. We're assuming x is real here. So in this case, we have two real functions. This is their product. So here, that's what we put in the integral, -1 to 1 over that interval. Go through it all, and that's 0. So yes, indeed, these two functions are orthogonal on the interval -1 to 1. We'll do this an easier way a little bit later, but this is just exercising that this definition. So now let's do a little bit more complex example that truly is complex. Let's take these functions here, f sub n, and it means this: e to the I 2n pi over big T times t. The argument is little t, not x here, but, and we'll look at it on this interval, which is just some interval of length capital T. Let's see what happens when we do these inner products. First, let's look at any function, its inner product with itself. Means we're putting it in this integral. That's the definition. Function times its complex conjugate, integrate it over that interval. Here's the function, here's its complex conjugate. Multiply these exponents, or when you multiply these together, you add the exponents. So this is just e to the 0, which is 1. Integrate 1 from c to c plus t, you just get capital T. That is the squared norm of any of these functions, regardless of what n is. Now, what if I do two different functions, say f sub m and f sub n? Here's what it means. So here's f sub m, and here's the complex conjugate of f sub n. I need to put this negative here. So again, I add the exponents, which means I get this. So this is what I'm integrating now. So we can integrate that. That's just e to an exponent. We'll divide by everything up in the exponent except the little t, and then evaluate what's left. Or then it'll still be this. Evaluate it between these 2 points. T equals c to t equals c plus capital T. What is it at C plus capital T? It's this times C, this plus capital T, which gets rid of that T in the denominator. I hope you follow that. That's pretty simple algebra. But now look at this thing from what we know about complex numbers. That's e to an integer number of 2 pi, which is always 1. And at the other end, at this lower limit, I just get the same thing as the upper limit. The thing evaluates to 0. So any two functions out of this set, no matter what is m and n, as long as m is not equal to n, they're orthogonal. Their inner products are 0. Now let's talk about orthogonal sets. Well, this is what it means to be orthogonal. You know, we take our two functions on an interval, and if the inner product is 0, they're orthogonal. A set, orthogonal set, is a set of functions, and usually we're talking about an infinite set of functions. And they're all orthogonal to each other. As long as you're looking at two different functions in this set that are orthogonal, that's what you call an orthogonal set. So we just showed that this set of functions, here I'm switching from f to phi and from t to x. Same thing here. This set of functions is an orthogonal set on this interval, which means any interval of length capital T. That's what it means to be an orthogonal set. We can generalize inner product and orthogonality by inserting a weighting function in this definition of the inner product, where that weighting function must be strictly positive on the interval of interest. And it would have a corresponding squared norm. A lot of the stuff we're going to do, this weighting function is just going to be 1. But let's look at things in general. I got time here. Can we expand some function as this infinite linear combination of an infinite number of orthogonal functions? Can we expand a function fx using an orthogonal set? Might wonder why we would do such a crazy thing, but that might come clear later in the course. But for now, let's just see if we can do it. First, how would you compute all these coefficients, C0, C1, etc.? Well, let's multiply each side by the same things. Let's multiply it by a weighting function and the complex conjugate of one of these functions. We'll say the phi sub n function. We're multiplying left and right side by w and phi sub n's complex conjugate. And then we'll integrate everything from a to b. We end up with this. But because this is an orthogonal set, all these phis are an orthogonal set. Anytime you have different functions, they evaluate to 0. The only one that doesn't evaluate to 0 is when you get the function in itself. And that is the squared norm. So we have a way to compute each individual C sub n. You know, this C sub n is going to be this guy on the left divided by the squared norm. So we have a way of computing all the coefficients. Can we really do this? Well, you also need another attribute, which is called this set must not only be orthogonal, but it must be complete. And that means there's no non-zero function that exists that's orthogonal to all these functions. So this set of orthogonal functions is all of them. There's no other function that's also orthogonal to all of them. We won't go about proving that. So here's what happens if the weighting function is 1, and it's especially easy when the e's, the functions are real. That brings us back to the Fourier series. We already showed that this orthogonal set, well, we already showed that it's orthogonal. We proved that. It's also complete. We'll have to express this on that. Which means we can express a function as this infinite sum of those functions, infinite or linear combination of those functions. And this guy is called the exponential Fourier series. We have a way of computing all these coefficients. By the way we just did it, it's this thing divided by the squared norm, and that squared norm was this capital T. So those are called the Fourier coefficients. So right here is the exponential Fourier series, a particular orthogonal expansion using this particular orthogonal set. I think I'll do the rest a little bit later. We'll dig into this Fourier series a little bit more in another recording.